Hi, I'm Eric Zivit, Professor of Economics at the University of Washington, and I will be teaching Introduction to Computational Finance and Financial Econometrics for Coursera. This video serves as a short introduction to the course and an overview of the class syllabus. So let me start with the course objectives. So the main objectives of the course are threefold. You're going to learn the mathematical and statistical techniques used in computational finance and quantitative finance. You're going to use the open source R programming language to analyze financial data, estimate statistical models, and construct optimized portfolios. Throughout the course, we're going to look at real data and we're going to solve real problems. The course material for this particular course is based on Economics 424, Introduction to Computational Finance and Financial Econometrics, that I've been teaching in the economics department at UW for the past 10 years. All of the course material is available on my class website, meaning the lecture notes, the class slides, and so on and so forth. So for detailed information about the class syllabus, go to the website. I will be giving sort of highlights of the syllabus as we go through this introduction. The Coursera website will contain the course videos for the course, as well as discussion forums, which will be monitored by TA and so on. Prerequisites for the course are the following. There are 4 types of prerequisites: mathematics, statistics, economics and finance, and programming. The mathematical prerequisites are 1 year of calculus through partial differentiation and optimization with several variables, as well as an exposure to linear algebra. In terms of statistics, I assume that students have knowledge of introductory probability and statistics course, preferably with the use of calculus. For economics and finance, I assume basic knowledge of principles of microeconomics, but no knowledge of finance per se, but primarily just an interest in finance and analyzing financial data. This course will heavily use the R programming language, so it's useful if students have some introduction to a programming language, preferably an object-oriented programming language. And so we'll be using R in sort of a rudimentary way. This is not a programming course in R, but we will use it for analyzing financial data extensively. In terms of the textbook material and other reading material for the course, the main source of material is a book manuscript that I'm writing with Professor Douglas Martin in the Department of Applied Mathematics. It's called Introduction to Computational Finance and Financial Econometrics. This is a manuscript in preparation, and book chapters in their raw form are available on the Econ 424 website. For those of you who like to have a full-blown textbook, I will also be following the book Statistics and Data Analysis for Financial Engineering by David Rupert. Essentially, the course material here covers roughly the first 9 chapters of this book. This is an excellent statistical treatment of financial data with integration with the R programming language. It's an extensive revision of an earlier book that he wrote called Statistics in Finance and Introduction. Because this course utilizes R very heavily, I also recommend 2 books for learning and using R. The first book is called A Beginner's Guide to R, and this provides a very gentle introduction to the R programming language from a non-statistical point of view. So it's just focusing on the language structure, how to use the language, and so on. And it assumes no knowledge of programming or of R as well. Very nice, short, concise chapters. I also highly recommend R Cookbook by Paul Teeter. This is a no-nonsense guide to R with essentially 200 recipes, for working with R, for doing data analysis, and so on and so forth. And one of the reasons why I like this book is because the author is a finance quant, and many of the examples in the book are geared towards the analysis of financial data. Now I'm going to go over the syllabus topics and say a little bit about each of the topics as we go through the course. So the course is going to start off with discussion of return calculations. The main thing that we're going to do in this course is to study financial asset returns. We're going to build probability models for these returns. We're going to estimate these models, and we're going to apply them to portfolio theory. So it's essential that we understand what we mean by the calculation of returns. Then we're going to do a fairly extensive probability review. So this is a course about the statistical analysis of financial data and computational finance and the like. And in order to be able to understand the material in this course, you need to have a good background in probability and statistics. So I do a fairly extensive review of probability concepts, starting with random variables and distributions, moving on to time series concepts, and a little bit of matrix algebra that's useful in statistics as well. Then the meat of the course starts with the analysis of financial data. So we do a lot of work with descriptive statistics. My approach to model building is to first look at data and understand the stylized facts of data, and then and the tools for doing this is the statistical tools of descriptive statistics and so on. So we'll learn to look at data, how to summarize data both numerically and graphically, establish a number of stylized facts that we want our models to be able to capture later on. So then we're going to move into the first model for asset returns, something I call the constant expected return model. It's a very simple model for asset returns, but it's very powerful and very useful because we can illustrate the model building process, we can state our assumptions, we can discuss the statistical analysis, how we estimate the parameters of the model, how we determine the accuracy of these parameters, calculate things like standard errors and confidence intervals. We can use the techniques of Monte Carlo simulation to simulate pseudo data from these models to see if the pseudo data looks like real data, which I call sort of the first step reality check towards looking at models. And then we'll do some computer-intensive statistical analysis. We'll find out that doing things like calculating standard errors may be difficult analytically, and we'll be using a technique called bootstrapping, which allows us to have the computer do statistical analysis for us. And then we'll apply this model to real data and evaluate how it works. And then we'll develop the statistical tools to be able to do that effectively. Once we have our first model for asset returns, then the main application of this model will be for portfolio theory. And this is essentially the theory for asset allocation. We're going to study what is a portfolio, how it's constructed, and then we'll be looking at Harry Markowitz's mean variance portfolio theory as a way of constructing optimized portfolios, or portfolios that are good in some respect. So we'll define what we mean by efficient portfolios from a mean variance perspective. We'll study how to construct these things mathematically. We'll study the mathematical theory, the optimization of how to compute these things. And then we'll go out to real data and apply what we've learned from our data analysis to portfolios and evaluate them. So after doing portfolio theory, we'll spend a bit of time on risk analysis, and in particular the notion of risk budgeting. And this is understanding the sources of risk in portfolios. So when you hold a portfolio with a number of assets, you would really like to know how much of your risk is being generated from one asset or another, and how can we summarize this. So that's the purpose of risk budgeting. And one of the features that comes out of risk budgeting is something called beta as a measure of portfolio risk. Beta plays a very important role in modern asset pricing theory, in finance and practice, by that manner. And then we'll end off the course with something called the single index model, which uses the concept of beta in a model for asset returns. In terms of homework and exams throughout the course, the Coursera framework is to have the lectures broken into little chunks with quizzes inserted after every 10 minutes or so to test concepts and knowledge. There will be auto-graded weekly homework assignments, some of them analytical, some of them programming, and there will also be auto-graded exams. Throughout the course, we'll be using the open source R statistical programming language. This is available free at www.r-project.org, and it works on all major computer platforms: Windows, Macintosh, Linux, Unix, and so on. So, and it's expected for students taking this course, that they will download this onto their computers and then follow along with the lectures and the homework assignments. The lectures and examples will utilize R, and many of the homework assignments will also utilize R. The exams, however, will not test you on your knowledge of R, but may present you R output, and then you would be asked to comment on that. There's a free add-on, which is an integrated development environment for R that I highly recommend, called RStudio. And again, this is also across all platforms. And this makes the working with R just a little bit easier than base R that you get from www.rproject.org. So I highly recommend the use of RStudio together with R throughout the course. I want to end this introduction to the course with a little bit about myself, so you can get an idea of what my orientation is and background. So I'm a professor of economics at UW. I'm also an adjunct professor of applied mathematics, finance, and statistics. My background, I have a bachelor's degree in economics and statistics from UC Berkeley, and I got my PhD in economics from Yale, where I my emphasis was in econometrics and finance. At the University of Washington, I'm co-director of the Master of Science program in Computational Finance, and I've also done extensive work in software development for the analysis of financial data. I wrote a book with a former student of mine called Modeling Financial Time Series with S+, and I'm working on the R version of this. So in terms of teaching, I've taught 19 years economics, finance, and statistics at the University of Washington. The graduate level, it's mostly econometrics. I teach econometric theory, time series analysis, financial econometrics, and risk management. And at the undergraduate level, I teach financial economics and computational finance. In terms of my research, it's sort of twofold. I do research in pure econometrics, development of statistical methodology, and more recently, my emphasis in financial econometrics, and in particular, the analysis of ultra-high frequency or tick-by-tick data, as well as the analysis of hedge fund data and risk analysis with hedge funds. I also do an extensive amount of software development work, originally in S+, which is the commercial version of R, or I should say R is the open source version of S. And then for the last 4 years, though, I've been doing extensive development work with R in particular. This course is also based on some extensive finance industry consulting experience. Part of this is in financial software development, and part of it is in industry experience with BlackRock Alternative Advisors, where I've worked on risk management consulting and the development of risk models for hedge funds. So this ends the introduction to the course, and I look forward to interacting with you this fall.